All right, so yay, now we're in recursion. So I know you've all heard a lot about it, and I guess it's actually not as intimidating. I think it's one of those things where you can probably understand how to do it on a pretty like usable level fairly quickly. But then if you want to kind of get deeper into it and learn more kind of more advanced concepts, it could take a little bit more time. So the way that we think about recursion, or like these, or at least like the easy book definition, right, is just a recursion that calls itself. Um, and if you think about it conceptually, it's like, well, I have a function that calls itself. Um, then once it calls itself, that iteration of the function is also going to call itself, and which is also going to call itself over and over again, right? And so the first thing that really should jump to mind when you think about recursion is, okay, so we have a function that calls itself over and over again. Like, when does it stop, right? At some point, things must end. Otherwise, you have a function that will go on infinitely. In modern day computing, they're actually fine because most computers have enough safeguards in place that will just like it will stop for you after a while and say, hey, I think you meant to like stop, or I think this is an error. In the old days, probably less so, right? You probably had less of a tolerance for error, and then you could actually use up your computer's entire memory if you weren't careful with recursion. Um, so anyway, whenever we think about recursion, the first concept that people really want to kind of focus in on, especially when we're looking at uses of recursion, is just what we call the base case, or rather, if my function is calling itself over and over and over again nonstop, when does it stop, right? Like that, and that base case tells you when it stops. If you remember how the setup of a while loop looks, which is like, while this condition is true, I'll keep doing this over and over again, right? And one of the things we talked about with the while loop was, well, every iteration of the while loop needs to get you somehow closer to the world in which the while loop becomes false and the while loop stops. And in this case, it's the same exact idea, right? Every time we run a recursive function, we should theoretically be getting closer and closer to when we stop. And when I look at your code, it should be very, very clear where we stop. Um, so we'll look at this in practice a little bit more, but just kind of drill in your mind at least that like the base case is probably the most important part of a recursive function because that does tell you when to stop. And whether and you might not like this, but if you write a recursive function, like the first question I'll probably always ask is, okay, so what's your base case here? And if you can't point to me where your base case is, then I'll say, okay, so you didn't really write a recursive function, right? Like a function that calls itself needs to know when to stop. And so if you're missing that piece, then it just means you haven't thought enough about what you're trying to get your function to actually do. Um, this slide, I won't go into the examples too much, but essentially it's just to show you that like most things in programming, there's probably more than one way to do a particular task. So on the right hand side, we have something that's that hopefully at this point is very familiar to you guys, right? It's just a for loop that counts down the numbers. In this case, in that function, we give it a number n, and it just counts down from n all the way down to 1, and then after we're done, and then this is the right hand side. We start with n, and then we do n minus minus. So we basically make n smaller on each iteration, and eventually we stop once we reach 0. So it prints out all the numbers from n to 1, essentially inclusive. On the right hand side, that function is doing the same exact thing. Um, and if I just kind of walk us through it, right? The idea is I have this function called countdown recursively. It takes a number, n, and then it logs it out on the first line there. And that's pretty straightforward. And then it does a check. It says, hey, if n is greater than 0, let's call ourselves again. Except when we call ourselves again, we'll actually feed ourselves the input of n minus 1. Else, the console.log says, hey, we're done, we're done counting down, and the function exits. So just looking at this like code on the left hand side, knowing that it does the same exact thing as the code on the right hand side, what's our base case there? Yeah. Um, yeah, and just to kind of refine a little bit, I would say the base case is when n is not greater than 0 anymore, because we have an if else loop, right? And we're saying if the if condition is met, we call ourselves again. But in the else statement, there's nothing, right? We console log and then we're basically done. And so when I look at that, it's pretty clear that like, okay, the if statement is going to be the base, or when the if condition is not met, then we're in the base case, right? And so That's what I mean when I say like when you look at your recursive function, it should be very clear to you like when we stop. In this case, it's clear that we stop when n is no longer greater than zero, and every time we call a function, because we're decrementing n by one, it means we're getting closer to the world in which n is going to be not larger than zero. So this is a part where so I'll probably do a little bit of diagramming about for this on the whiteboard. But this just kind of tells you that in JavaScript, or rather in most computers in general, when we talk about synchronous functions, the idea is that things have to go in a certain order. And what I mean by that is, if you think about how a piece of JavaScript code that anything we've written so far, really, we think about how it runs. The idea is that we take it for granted that it runs in a certain order, right? And most importantly, what's valuable about that is we're going to assume that that a line of code will not run unless what's supposed to run before it has finished running, right? So if we console log, I'm about to start a for loop, and then I have a for loop, and then I have a console log after that says, hey, my for loop is done. My for loop is done will not run until after the for loop finishes, right? And so by that, what we mean is it's synchronous, as in the computer is very explicit at a certain point about, hey, I'm going to run this, then this, then this, then this. There's a very set order, and I know what that order is ahead of time. The opposite of that, and this is more for your information than anything to do with this class or the assessment, but if you think about the world, actually, a lot of what we do is actually asynchronous. And what I mean by that is, if I load up a website, right? If I load up Facebook, I actually don't know how long it takes Facebook to get their data to me, right? Maybe they're doing some really heavy calculations before they show me my newsfeed, and it takes them like 30 seconds. Or they could have it cached somewhere and super fast, it takes half a second, right? So that's an example of asynchronicity, whereas like if I want to do something and I'm not quite sure how long it's going to take, but I want to be doing other things while that parallel process is going on, that's an example of a world in which things are not synchronous, right? As in like you don't really know the exact order in which things are going to be happening in. But for our purposes, and for everything that we've seen so far in this class, and you probably will see, at least up until like probably midway through, the first half of the immersive program, everything's we're going to assume is going to be synchronous, which means that if I look at the code, I know for a fact which code is going to run in what order, and what happens next is pretty straightforward. What this slide is asking is basically saying, well, if you think about a recursive function, right? A recursive function is going to run, and much like a for loop, it's going to keep running until it stops, which means any code after it will not run until the recursion finishes. And so now we see kind of one big danger of recursion, which is that if the recursive loop never finishes, not only is that loop never going to finish, nothing after it is ever going to run. So let's talk about how we kind of manage this order in computing. The short answer is we have something called a call stack. The call stack. There's a bunch of ways people describe it. You can think of it as like a stack of pancakes. I like the idea of like a stack of plates at a buffet, where it's the idea that like if you were to grab a stack of plates at a buffet, typically speaking, you always grab the plate that's on top of the pile, right? You might think the one on the bottom pile might be cleaner, but you're not going to lift up like 30 plates, grab one from the middle, and then put the rest back. At least in general here, right? So the idea of a call stack is, hey, whatever is put last, or whatever the latest thing put on the stack is, that's currently the most important priority, right? And I can't move on to the other thing I do until I finish that one first. So let's draw something like this, right? So when I think about a call stack, and this might seem a bit, sometimes depending like on how in detail we go. Okay, so this is a call stack, right? And you can think of it as your computer priority list. Like, hey, so what do I do now? What am I working on right now, right? If I have a function that just says something like this, let's see, I call it console log. I'll just say console David, right? And then afterwards it consoles how the computer thinks about it, right? The computer's like, okay, first lines first, console David. So it's like, here's our plate, right? And the plate is console David. Now, at this point, it says, okay, I have one thing called console David. Can I do it? And the answer is, yeah, I'll just console David. So then it basically says, okay, at this point, this is the only thing on my priority queue, and I can do it without needing anything else. So I'll just do it. And it does it, and then it kind of takes it off the priority queue. So now it has like a clean plate, or a clean queue here, right? And so it already did the first line of code. So then now it says, okay, great, I finished that line of code, I executed it, perfect. Let's go to the next line of code. Console fs. Same idea. We come here, we console fs. It says, okay, great, do I need to do anything else? No, you have all the things you need to do this command. So the computer says, okay, great, I'll do it. So it does, it consoles out fs, and then it finishes. And then it looks and says, oh, I'm on the last line of code, there's nothing else to run. Okay, I'm done, I'm gonna go. Right? So in the most basic example, that's how a console log, or that's how a computer thinks about executing lines of code. However, one of the things that one of the reasons why this example works in this here is because console log just says, hey, I need to console log something, and it's not really depending on anyone else to do anything for it, right? Like it's like a kind of a one-step procedure. It's like if I said, hey, can you hand me that stapler, right? You just give me, assuming there's a stapler in front of you, you just give it to me, and you're done. Now, what if I said, no, can you get me a coffee, right? Or can you get me like a latte? Well, something like that requires more steps on your behalf, right? Unless you can maybe assuming you don't have a latte in front of you, it is okay, I'll get you a latte, but I need to go to Starbucks, buy a latte, come back, bring it, and give it to you, right? And so in that case, there's a lot more steps to know that you have to do here. And basically, each of those steps is, for now at least, we'll think of it as being represented by a function call, right? So let's look at this this lines of code here, right? We have basically 4 variables being declared, right? And once again, all we're doing is saying, hey, these variables exist. Up until this line, everything above my hand here, we're not running anything, right? We're just saying, hey, these functions exist. We don't know what's inside of them, and we don't really care for now, right? We know that these functions exist. That's it. Then we get to the last line here. It says, oh, run readme. And now it's at this point the computer says, oh, goody, like now I'm actually going to be doing something, right? Yeah, you're actually giving me a command to execute. You're actually giving me the function to run because, again, open and close parentheses, right? So the first time it'll do it, it'll say, great, let me now run meet me. Okay. And so looking at the meet me function, what the computer says, okay, great, let me just run it. Oh, shoot, before I run meet me, I actually need to do what? Right. My next thing is, if this is a console log out, whatever, I can just do that and I'm done and happy. But it says, actually, David, you can call, or rather, from the computer, it's like, actually, I needed to call another function first, right? And so now you see how this is an example where meet me really can't finish unless it calls another function first. And so now here's where we start building up our priority queue or our stack or our pancake or however you want to phrase it, right? This is required to say, hey, before you do that, you need to call say hello. And notice how I don't even worry about say how are you yet, right? And the reason why is because remember, computers run in sequence, right? Like this say how are you cannot run unless say hello runs first. And that's right, unless say hello finishes, right? Similarly, it goes like this line has to finish, not just start, it has to finish before the next line of code starts running, right? It's a very orderly process. And so the reason why I'm saying let's say hello here is, hey, we need to finish say hello before we even worry about say how are you. Does that make sense, everyone? We're good? Cool. So let's take a look at say hello. I'll go from the very first page. What does say hello do again? Okay. Do I need to call anything else? Is it dependent on any of the functions? Oh. No. It's just log out hello and you're done. So let's just put let's just assume that this is the one. assume that this is my console, okay? Okay. The first thing I'm going to say is log out what? Help. Hello. Okay. Hello. Okay. That's my line one. And in fact, I am executing say hello. So now at this point, after I log out hello, is say hello done? Yeah, it's done, right? Like I call say hello right here. I log out hello, right? And there's no next line. I reach the end of the curly brace. My function is done executing. Cool. So now that means I just finish up with this particular plate, right? Notice how I'm only erasing say hello for now because I can't erase say Mimi because Mimi isn't done, right? Mimi still says, great, say hello, finished. All right. The next line I'm trying to run is actually say how are you? And once again, it's another function, which just means I need to go and say I'll say H are you? How are you? Okay, just make sure it's right. And now I go up to say hey, say how are you? So what does say how are you do?
It calls wait for response and then prints its own text.
Okay, right. But I guess like let's just start with wait for response first, right? Because it needs to call wait for response. It's not going to print its own text until wait for response finishes. And as of right now, I don't actually know what wait for response is, right? Like it could something take a minute, take an hour to do whatever it is. Whatever it is, I know that I cannot console log how are you until wait for response finishes. So that just means here we have another kind of plate arm call stack that calls out wait for response. WFR, wait for response. So now we come all the way over here to do wait for response. And what does wait for response do? You just console log out waiting for us, right? Everyone see that? Right? Wait for response. Great. After console logs out waiting, wait for response is done, right? We've run the entire function, we reached the end of the curly brace, and there's nothing else for us to do anymore. So I actually kind of confidently say, okay, great. This job is also now done. And if I look at my next priority tree, says, okay, great. Before I was running wait for response, I was trying to run say how are you, right? And I come back here, and now to Lawrence's point, say, okay, great. Wait for response is now finished. I check off this line of code, it's complete. I then now console log out how are you? And once I console log out how are you, that means say how are you is also done, right? I reached the end of the say how are you function block. I cross this off, or I wipe it clean. And now we're just getting back to again. I'm pointing at the answer, guys.
After how are you?
Yeah.
Then we're finished.
Well,
We get with this one.
so remember with functions, right? We always go back to where we call the function, right? And so where we call say how are you was the last line of meet me. And so now at this point we say, okay, great, how are you finished? By the way, who called how are you? Where I leave off? I left off at meet me. Okay, great. I'm back at meet me. Say how are you is finished, and now I'm actually done with the meet me function. So now finally I can cross this off my plate. I look off for the last line. Said, yep. All right. Meet me was called right here, and there's no code afterwards. So now my queue is clean, and as a computer, I've done going through this line of code. Right? Notice how at this point, and this is something that is, I can't stress enough about computers, right? Computers essentially live in a binary world, right? Everything is yes or no. Like it's very clear what it does next. There is no ambiguity. There is no there is no sense of oh, like maybe I'll do this, maybe I'll do this. And I know like I get a little bit tough on some of you when you ask questions, right? And I try to ask you I make you ask super direct questions. Because ultimately like in programming, like a lot of times that's what it comes down to, right? Is you can't ask vague questions because computers are actually terrible with vagueness, right? But hopefully this shows you computers are what they're really good at is saying there are two discrete choices. I do one, then I do the next one, then I do this one. It's like super logical, like extremely logical. Right? So when I ask you to like make your questions more refined or kind of make your questions more pointed, it's not to just be difficult. It's to say when you see your code not doing what you think it should be doing, like you need to understand how to ask those questions. Right? Those questions should not But if you say the computer is supposed to print out this and it's printing out this instead, now we have a very clear disconnect and we can start investigating that disconnect, try to figure out where it's happening now. So does this call stack make sense to folks about how we're doing this and what order things go in? Great. So that's what this is. Okay. So steps to writing a recursive function. One is define the base case, and once again, base case. It's by far the most important part of a recursive function. We also define the recursive case, which means, great, I know when to stop. Obviously, the other question is, when do I keep going, right? And for a recursive function, really, at the end of the day, like, that's kind of like, there could be other decision points in the code, but at some point, like, this decision point between number 1 and number 2 is always going to happen, which is, when do I stop? When do I keep going? Right? Like that decision tree is always going to exist in every recursive function.
Isn't that kind of the same thing?
As
Like the recursive case and the base case isn't not the same thing?
Yes and no. Cause like, so let's say I choose to stop, right? At that point, I'm terminating this particular iteration of code. But if I don't choose to stop, I can also call another function instead of calling myself. So there's different ways I can execute the code. But ultimately, like, it's like you could have like more than 2 paths, but these 2 kind of always need to be there. Like, you need to have at least these 2 paths in every recursive function, which is, when do I call myself? Because if you don't, then you're not a recursive function. And then when do I stop? Because if you don't stop, then you're just not a function. And then you also have, like, oh, what if I call another function somewhere else for another purpose? Like, that's also very valid. But anywho, these 2 are the base minimum requirements for a recursive function. And then 3 is kind of not very useful, but just write code. So that's kind of where you do the thing that you're actually trying to do with your recursive code. So I think that's it for the slides, right? Or no? Okay. So for this one, rather than writing out the code, let's just do a stack trace for it. And so here's what I'll say. Like, that code is correct. That's gonna run. And I'll probably just have volunteers come up and like draw the call stack for me. That'll probably be easiest that way. If who wants to volunteer, this is your plate. Right?
The one on the screen?
Yeah. So in this case, can you try to do it the way that I was doing it, where it's like, I'll probably just have you do like a few lines of it. But okay, so where are you starting? Where are you starting right now?
We are starting with the original call, which would be factorial 5.
Actually, sorry, give me 1 second here. Let me just. I'm actually gonna put this on a repo so it's easier for us to see because we have line numbers and can follow along probably a little bit cleaner. Okay, so the first line is you're at factorial 5.
Yes.
Okay, so does everyone agree with where Lawrence is starting right now? Okay, Lawrence. So walk us through line by line what's happening.
Factorial 5. All right. First off, n is being fed in is equal to 5. If n is equal to 0, return 1. It is not. Otherwise, we will return n times factorial n minus 1. So n is currently 5. So we're going to have 5 times 5 minus 1. So we're going to return 20. Actually, we're not returning yet. We're returning 20 within. Okay, I'm seeing it now. So
How about this? I actually need to go cough real quick. But as a class, discuss amongst yourself of kind of like how you think this factorial tree is going to play out. I'll be in the back watching once I get back. But yeah, so crowdsource solutions here. But ideally, I want you guys to be able to kind of draw a call stack of how this actually looks to a computer in real life. Okay.
So currently, I think that just for convenience and helping us out, we can ignore the return part here and focus just on n times factorial. So factorial is getting called again, but this time 4 is being fed in, not 5, because we have 5 minus 1, which is 4. So we now have another case of factorial. Sorry about my awful handwriting, by the way. But this time it's having 4 be fed in. On the outside, we have it being multiplied 5 times factorial 4. Is everyone agreeing with this? Any disagreement?
Yeah.
Okay. And I think we can just continue in this spirit. So it's going to be 4 times factorial 3, and then 3 times, and etc. Is our goal just to draw out the stack, or is our goal to determine what the output's going to be? I'm actually asking you, I don't know.
I guess both.
Is the goal to draw the stack or determine the output?
Draw a stack. Let's see how. Okay.
Because it's actually what I have.
So the last line becomes what?
What do you mean the last line?
The last line.
So the top one is factorial 2, above that we have factorial 1, and we'd stop at 0 because it stops when it equals when the input equals 0. Okay, so we actually would have factorial 0 trigger. Is there an eraser anywhere?
Yeah, just paper towel something.
Is everyone following what I did here? Okay, are we correct?
Okay, so now you have this Q, right? And your
Yeah.
Q should be an N. What's your base case?
Base case is when n equals 0.
Okay. So now, as a computer, let's work backwards. Let's unravel that. So as a computer, you can't have that, right? You need a clean slate.
Converted.
So you actually need to actually run the code. So how does this work now?
How does this work? Alright, so we are feeding in 5. 5 is not equal to 0, so we're going to run another case of factorial, but this time with 4. 4 is not equal to 0, so we're running n with 3. 3 is not equal to 0, so we're running n with 2. 2 is not equal to 0, so we're running n with 1. 0 is equal to 0, so we return 1. And then that shoots back up.
So you just kind of so what you're saying is at factorial of 0, what happens?
At factorial of 0, our base case triggers and we return 1.
Okay, so let's mark that somewhere.
Okay, so our new return. Return is equal to 1. And our next case.
Sorry, are we going to start actually from the top now?
What?
According to what you said before?
Uh,
The computer will is going to start doing
Yeah, the top of the stack.
from the top of the
Right,
stack.
so we always do whatever is currently at the top of the stack, yeah, sure. Unless we put something else on top of the stack, in which case we do that instead.
So then we would multiply 1 times 1, and then that's done. We take that result and move to the next one.
Yes, we keep going. So in this case, we are going to do
2 what?
2 times 1, so our return.
Okay, so right there, so that looks wrong because you can't be doing the second layer of a stack if your top layer, if there's a stack layer above it, right?
The stack layer is known as return 1.
Okay, so is it part? So why is it so part of the stack then?
Oh, so we erase it then?
Well,
If we know that it's not, we know that it's not.
but you have to erase it because I guess when you draw this out conceptually, and this example might be even simple for us in terms of walking through as a class, but you need to realize when you finish a line of code, right? Computers will never run things in the middle. They're really bad at that, right? They always start at the beginning or the end. And so in this case, we're saying I'm only ever going to run code that's at the top of the stack. Okay, so now where are we at?
We return 1. So now we have 2 times the previous return of 1. So it's going to be 2 times 1, so we return 2 and eliminate this layer of the stack. So we have 3 times the return. So 3 times 2 is 6. So we return 6 and erase this part of the stack. And then 4 times 6, which is 24, if I'm not mistaken. 4. And we can get rid of this part of the stack. Now we have 5 times 24. It's going to be 120. Return. And 120. And now we have factorial 5. Is going to be 5 times 120, which is 600. And we're done. It's going to return 600.
Okay. Does anyone in the class disagree with that? Do you agree, Kaz?
Sorry?
I love how like I asked, does anyone disagree with that? You don't say anything. Like I ask you, do you agree with that? He's like, no, I don't agree with that.
No, you asked if I agree with that. No.
Well, I asked the class at first, and no one said no.
Where did I goof up on my math?
You return 120. That's it.
Oh, you don't return 600? But are you doing 5 times whatever the output of the previous factorial is?
You messed up the top steps.
So what's factorial 5
1 times
returning?
1, you missed 1 times 1.
Factorial 5 returns its input times the output of the previous one.
Okay, and
You
so
missed 1 times 1. Factorial 1, and then when it goes to 0,
Oh,
it's 1
okay.
times 1.
So in that case, we're just returning 120. I get it now.
Yep. Just add the
okay, so where the math kind of went wonky is not at 1 times 1. It's at the very last step. Factorial 5 is 5 multiplied by factorial of 4.
Yeah.
And so I guess like it's easy for us to say numbers in terms of like very like, oh, it's just 24, but like would like the way you want to say is like, okay, factorial of 4 returns 24, right? So because like at the end of the day, like when you remember like what a function is really what really matters in a function is ultimately what it returns, right? And when we talk about recursion, it's very much like you need to really understand what your function is returning, and also where you're returning it to, right? So just even looking at your math, right? Like the quick pattern is, oh, it's whatever factorial I'm at, it's factorial of n, it's n multiplied by factorial of n minus 1, right? So factorial of 5 is 5 multiplied by factorial of 4, which you do that, right? On that current stack on the high stack you have now. And then when you have factorial of 5, you're like, oh, let me just multiply it by 5 again. And that just shows that why are we multiplying again? Like that's not part of the code, right? Like that's a human assumption of like.
That's because of the way I visualized it primarily.
Well, I think you actually visualized it fine because but I think yeah, like basically like it's like like when we do a function, when we do a recursion call stack, like yesterday I made kind of a point about this, but it's like the return of a function is something you be very, very, very precise about because computers are going to be very, very precise about it. There's no like wiggle room there. And so when you return a function, just be very clear about where you're returning a function to. Dustin, you look confused.
Yeah, I have another question.
Okay.
I understand what you're saying. That's fine. I don't have any problems with
Cool. All
what
right, thanks, Lawrence. Sorry, what was your question? What's your question, Dustin?
I mean, maybe this is kind of dumb in the very beginning, but I mean, the function factorial. Okay, the word factorial there, is that just standing in? I understand what a factorial is, but I don't understand, I guess, this line 5. If the word factorial means take the factorial, 5 minus 1 is 4, and then the factorial of 4 is going to be 24, right? Wait, the factorial, 4, 5, that would be, so then 5 would be, the answer to that, let me start all over again. If I take 5 and I put that, yes, that's better. Okay, that makes a lot more sense. Because I was getting confused about where to do the factorial.
So in JavaScript, unless a word is in blue or red, it has no meaning. It's just a variable, right? So function has a meaning because it's in blue. It means it's a reserved word in JavaScript, which means you cannot overwrite that with your own definition, right? I know like factorial means something mathematically in the human language, but in this case, it's just a variable, right? So when we think about like I think this is one of those things where it's like with like when I think about like you think about computers, they're just like extremely precise things, and so like I guess you can't just see something that says fact. Or actually, let me put it this way: if the word is not highlighted in like blue or red, or if it's not capitalized, usually that means it's just a variable, and you should try to figure out where that variable comes from. but yeah, okay. So yeah, so let's call it something else where it's maybe not as confusing or there's not as much of like an English equivalent to it. But I guess like, does how we ran that code make sense to the class? Justin, good?
Yes.
Becky, you good? All right. Well, if no one has any questions, I mean that's the entire lecture right there. And if everyone got it, then this workshop should be a breeze, right? Cool. Yeah. So small tips for recursion. Console logs, great. Just print out as much stuff as you can. Um, Using smaller inputs is usually better than using big inputs for testing in general, not just for recursion, but for all things, unless you're trying to test big inputs specifically. And the reason why is, if we test recursion 5, we can pretty quickly figure out if our math is right or not, right? If we test recursion 100, that's pretty heavy load on the computer, and it's not going to give us any it's going to be a lot more difficult to get us essentially the same exact answer, unless for some reason we think this recursion is going to break for large numbers. So using smaller inputs is usually just like better and faster and more effective. Um, yeah, if you get stuck, try writing the function aerially first. Don't Recursion is a tool, just like anything else, right? You might not have to use it. For this workshop, obviously write everything recursion because we're trying to practice recursion. But just know that in the real world, it may or may not always be the best solution. And then lastly is try drawing that stack. I know it seems silly, it might seem a bit redundant, but try drawing that stack. And if you have a question for me, like I'll probably ask to see how you drew your stack first to make sure that you're actually tracing the calls in the right order. Yeah. So any questions on recursion? All right then. Let's have at it.